So, welcome back student. We are basically discussing stereochemical based strategies, and on that particular point we are mainly focusing on substrate directed strategies. We said substrate directed strategies are those where you have a pre-existing stereocenters in your substrate. So, the pre-existing stereocenter in the substrate that basically controls the incoming reagent in such a way that your existing stereocenter is now determining from which phase the incoming reagent will attack. So, we already explained that if you have this kind of cyclohexenol system in a as a beta alcohol, you can control the epoxidation through a substrate directed mode and you can get this beta epoxide. Those 3 stereocenters you can basically fix. Now, I am giving you a similar kind of approach. Can you synthesize the other diastereomer starting from the same starting material? Now, here it will be little bit seems to be little bit awkward, because substrate directed probably you cannot have the hydrogen bonding thing. Initially what we said? We said that your substrate does have a well defined geometry in the ground state, then your MCPBA, the whole thing, it is basically attacking from the top face. Now, here you are basically instructing that we need this epoxide forms to be the bottom face. In this case, the main way is first you make sure the alcohol has been protected with a suitable protecting group. The more bulky the protecting group, it is better, bulky protecting group. So, what you do? You first protect this compound as a bulky protecting group like tertiary butyl diphenyl silyl, SEPH, PH, means that now try to draw its ground state half chair form. Now, you are basically having this Si, this tertiary butyl is there, this phenyl, this phenyl. In earlier case, that free hydrogen that basically makes a hydrogen bonding with the reagent. So, here this free hydrogen is now missing, and eventually this presence of this bulky silyl protection group effectively blocks the top face. So, then now MCPBA ARC double bond to OOH will now effectively attack from this alpha phase. And this is very obvious. You react with this fashion, you get this alpha epoxide. Now, simply remove this PG to get the required diastereomer which is desired. So, this kind of so the initial approach is the first one where you have a hydrogen bonded, it is called substrate guided. The second one which we have just now talked is basically a steric guided approach. So, these two parameter is very important, and in one case you are having this hydrogen bonding interaction which basically directs the incoming electrophile. In another case you are having this steric directed approach. The substrate directed approach next will try to focus on a similar kind of problem which is also very interesting. I am now saying that okay, I am having this compound or this compound, any of this enantiopure compound. Now, I am saying that is it possible from this compound to prepare a 1,3 dihydroxy compound, either this or this one case is syn isomer, another case is the anti isomer. So, is it possible? I am saying it that syn and this is anti. The answer is very much possible. The answer is very much possible, and you have to take care of this initial configuration of this starting material. So, now what I am trying to do, we will explain this scenario, and this is basically example of a 1,3 induction. Now, so the starting material we now write, the starting material is, so you are basically trying to reduce this carbonyl. Now, this carbonyl is 1, 2, 3. Now, existing stereocenter is 2 carbon away. So, it is a 1,3 induction. Now, what I am saying that you basically devise the reaction pathway. So, I am saying that if the pathway it's follow a 6-member transition state, and where R1 and R prime will try to having a equatorial kind of orientation, then you this OH will put it here, and then I am saying if this OH is available for some coordination with some reagent, something like some reagent which will now simplify later on, and if this reagent is having a metal center as well as the hydride, probably this one can give you the, this is the carbonyl. Okay. So, I am saying that if, so this is the compound written here, OH is below, and then you write the 6-member transition state where R and R1 is put in the most stable equatorial form, carbonyl we fix it like this, and then if this OH is available for this coordination with this metal center, I mean if you have a metal containing reducing agent as well as this metal containing reducing agent can give a internal hydride source. So, this hydride can only attack from this side, and then the relative OH is, this is below, this is above. So, basically we will get the anti alcohol. This is we called internal hydride delivery, internal hydride delivery. The same line you may have another scenario, what you can now design the carbonyl, we now put it in this way, and then put this oxygen here, and then I say that if some reagents are here where carbonyl oxygen as well as alcohol oxygen both can coordinate. Now, if you use a external hydride source, this hydride will only have this option to attack. So, this is a external hydride delivery. So, in this case now if the reaction goes, both are seen, this is below, this is below. So, this is you get anti, this you get syn. The first reaction, the syn reaction now is known as Evans Saxena reduction. It is kind of a now very famous name reaction, the substrate directed reduction, and the second one is now named as this external hydride delivery Prasad Narasaka reduction. Now, the reagent system now we will be talking about what are the reagents exactly you need to use. In case of the Prasad one, if you now draw the transition state again, the reagent system basically which was used a ET2BOME. Now, this ET2BOME basically ET it is a ET2BOME and sodium borohydride was used as a reagent if you want to do the external hydride delivery for this reduction. So, now this reduction ET2BOME, this boron, one methox is there. So, this methox is replaced by this alcohol. Now, this boron coordinates with this carbonyl Lewis basic site and then ET is there. Now, this NaBH4 transfer this hydride from this phase. So, now you get the syn alcohol. Now, if you have the parent alcohol is this way, you will definitely get the other syn enantiomers whose stereochemistry or syn diastereomer basically you will get this. As obvious, the same way the mechanism will operate. So, this is the Prasad-Narasaka reduction. Prasad-Narasaka reduction. It is very famous, and the only thing is you basically take this corresponding beta hydroxyketone or alpha hydroxyketone whatever you require, you react with ET2BOME sodium borohydride. Now, these reagents are not chiral, substrate is chiral. So, now this kind of transition state will operate and will give you a external hydride delivery to give you a enantiomer pure compound where 1,3 asymmetric induction will takes place, fine. And now, this next one, this Evans-Saxena one, Evans-Saxena reduction is on the similar thing, only difference is you have a internal hydride delivery. So, the reagent which was now required should be producible or should be producing a hydride from internal sources. Now, you basically use a tetramethyl ammonium triacetoxy borohydride. So, Me4N plus, or you can use sodium triacetoxy borohydride NaBH whole thrice NaBH. So, NaBH whole thrice. Now, the reaction basically goes through this kind of way. The same thing, we put the oxygen here, the boron is here. Now, the carbonyl basically will here. Now, this boron is basically a negative charge here because it is tetraacetoxy borohydride, and then this gives you these things, and one of these acetate was first replaced by this alcohol. Okay. So, then you are basically having a hydride which was there in the initial reagent, and then you get the internal hydride delivery and you basically get the anti-alcohol. And in this particular case is very useful, and you get a absolute good stereocontrol for this kind of asymmetric induction. It is a pure case of 1,3 asymmetric induction. Pure case of 1,3 asymmetric induction. Now, our substrate directed approach probably ends here. There are definitely many more examples, but please try to go through the assignments which will be supplying and try to get more knowledge from the assignments. Next guideline in the stereochemical strategies we said will be now try to focus in on desymmetrization. Now, desymmetrization we have earlier explained, and at that time we only talked about achiral desymmetrization. Now, we will be trying to focus it out on chiral desymmetrization. Now, desymmetrization is basically very important strategy where you can find that if you are having a molecule which can be efficiently desymmetrized to give you 2 enantiomers, then it is absolutely useful. We will come back to our simple example which we also earlier explained, that if you have a compound like this, is a prochiral compound. Okay. Now, what I am saying that you have OH1, OH2, these are enantiotopic we explained earlier. Now, I am saying that okay, you try to first do some reaction in this OH1 in a chiral fashion. Chiral fashion means this compound is a prochiral, this compound is prochiral. Now, I will try to put this prochiral compound in a chiral environment, same like chiral resolution or kinetic resolution takes place. Now, what happens, this OH1 and this OH2 are basically enantiotopic. So, they might interact with this chiral atmosphere in a different way. And eventually, just trying to give you the proof of concept, probably the what exact reagent, what exact catalyst system is we are using, it is probably beyond discussion of this particular coursework. Probably a very advanced level coursework will help you, but and if you are if you wanted to know in detail, we can just supply you some study material. So, now I am saying that you try to put a chiral environment for both this compound, and I am saying that one case OH1 this enantiotopic group reacts, and one case this OH group reacts. Now, if this compound reacts, initially is a symmetric compound. Now, you are basically having a this stereocenter now will be different. So, I am saying that okay, this prochiral reacts and you get some compound which is now this. So, OH1 reacts. Now, in this case I am saying OH2 reacts. So, if OH2 reacts, now if OH2 reacts, you get this X and this OH1. Now, OH1 and OH2 basically is both are OH. Now, you try to analyze their relationship. You can simply have a plane of mirror plane, these two are basically enantiomer, these two are ent. If it is ent A, this will be simple A, means enantiomer. A and A are this A are enantiomeric. So, basically this kind of reaction we called chiral desymmetrization. Now, as this desymmetrization give you a enantiomeric compound, we call this as a enantiomeric desymmetrization. Enantiomeric desymmetrization. Now, enantiomeric desymmetrization sometimes also it is very important. If you try to give you another terminology, we will explain another terminology which I am now saying is enantio divergent. Now, this desymmetrization and enantio divergent are basically in principle very similar concept. Now, what are enantio divergent route? The enantio divergent route says that, as the name implies, diverge means this route is basically kind of a two different way. You start with the starting material, and if you get both the enantiomers of a same product, then your route is called enantio divergent. Now, in usually what was done, you take the starting material, The starting material could be prochiral, could be achiral, but as we are talking about desymmetrization, it could be prochiral. So, you basically do a FGI, you get some intermediate 1, you do another FGI, you get the product. Let us say you get a plus product. Okay. Now, in this whole process, if one of the intermediate, you can basically do some stereochemical sense changing either by inversion or by mutation, you may get another intermediate. Now, this intermediate is basically will lead you to a negative or the minus product. So, in principle, starting from same starting material, you can get both the enantiomeric product, and that is why this is called divergent. And in principle, this is very useful because depending on your need, if you need both the product, both the enantiomeric product starting from a single starting material, you can basically reach to your final destination. So, initially we will try to have a example through a very simplified problem. I will say we will take a symmetrical compound, because the concept is desymmetrization. So, now this is a very nice example of desymmetrization coupled with divergence, enantiodivergence, desymmetrization plus enantiodivergence. The starting material which I have taken is a racemic one. So, means this isomer as well as its enantiomers are present. Now, if you see this compound is having nice sigma V. It is basically a meso compound or internally compensated. Now, normally meso compounds we said those are optically inactive, probably you cannot use meso compounds in some synthetic transformation because they are regarded as achiral. But you see closely, these two OH groups are basically enantiotopic to each other because they are enantiotopic, because they have a mirror image symmetry in between. Now, what I am saying, okay, we already know that CDA technique we have earlier explained. Okay. Now, I am saying as both the OH are enantiotopic and their reactivities are almost similar, we will react with a chiral isocyanate with this one as well as this one. Fine. So, what we will now get? So, for if you react with this OH, you will basically get O, CO, NH, R prime. R is basically chiral center, and then for this one also you get the O, CO, NH, R prime. In your reaction mixture, both the compounds are present. Okay. Now, if you try to analyze, this is the unique desymmetrization reaction, because these compounds are now diastereomer, because you put a chiral center here R. So, these are no longer enantiomer. Okay. So, enantiomers, initial enantiomers or the meso compounds are now converted to the corresponding diastereomers. So, this is now dia, these are basically having diastereomeric relationship, diastereomer and diastereomer to each other. Now, as we said, the diastereomers having different physical properties, so they can be in principle separated out. So, fine. So, what we next do? We do a simple protection here, OH, we put a protecting group here, we put a PGO, and then remove this carbamate by lithium aluminum hydride, basically get this OH. And then here also you do the same thing, you do a protection at this point and you get the lithium aluminum hydride reduction. Now see what is this? These compounds are basically now mirror image. So, starting from a meso compound, you have separated out this meso compound through a chiral desymmetrization or a enantioselective desymmetrization just by making a chiral derivatizing agent. So, this is a very useful technique and eventually this whole pathway can eventually lead to a series of reaction you can basically think about, and probably you can take it as a home assignment how both of these enantiomer can be converted to this lactone. From this compound you get this lactone and from this compound you get this lactone, and actually these lactones are basically mirror image to each other. So, this entire pathway is desymmetrization as well as divergence, and actually this particular technique is often named as meso trick. Meso trick means utilizing the meso compound and its internally compensated chirality to make two diastomers. Now, these compounds are in reality these are not diastomers, these are basically pseudo enantiomers, because if you cleave this NHR, these are basically separated. The only thing is you need to react with a chiral derivatizing agent, so that the diastomers can be easily separated by physical separation. Then you do a simple protection, so you can basically get these two enantiomers. So, this is a pure divergence and this method is called meso trick, and in principle you can basically convert these compounds to this lactone, this compound to this lactone, these lactones are enantiomeric to each other. Now, I am not explaining it, but probably one example one case I can show you the example how you can do it, because the reaction we already know. I am saying that okay, this first case you take this OH. This compound is allylic alcohol. The reagent which I will be now using, all of you probably know it, this reaction we have explained many times. We will be using a Johnson Orthoester-Claisen rearrangement, and Johnson Orthoester-Claisen rearrangement, the information is it is a substrate directed reaction, the 3,3 sigma atomic reaction. Whatever stereochemistry of the alcohol is having, when you make this new carbon carbon bond by the Johnson Orthoester reagent, basically you will get these things after this Johnson Orthoester rearrangement, and this carbon carbon bond is now going to be formed newly, and this stereocenter is basically whatever stereocenter is there, this alcohol has been retained, is called complete retention of stereochemistry. Now, as I am not explaining the mechanism of pericyclic reaction and its stereochemical features, we are not discussing it, but just remember. So, once this has been done, it is very simple, you remove this PG, hydrolyze this CO2 ET by NaOH, you can basically get one of these lactone which was here. From the other enantiomer you can get the same reaction sequences. So, basically what we did, we take the meso compound, and we assume that the meso compounds have similar chemical reactivity, not assume, this is sure, these compounds will have similar chemical reactivity. This basically we just reacted with this chiral derivatizing agent to get the diastereomer. We separate out the diastereomer and then we get this two compound which are basically enantiomer to each other. So, meso compound's chirality has been internally compensated, but we use that internally compensated chirality to separate out two enantiomers, and this is basically a enantio divergent approach through a desymmetrization pathway. It is very useful, and we can subsequently see how this divergence is very helpful in our subsequent pathway. So, we will basically continue our discussion on enantio divergence, and we will do it in the next lecture. So, please go through the slides and have a clear cut idea about this divergence, and try to go through the assignments which will be supplied with this lecture. So, till then have a good time and goodbye.